Chapter 15, Conjugated Systems. What are we going to learn in this chapter? We will learn what conjugated systems are about, how come they are stable. We will learn also some chemistry. Three main reactions in regard to this chapter. One has to do with conjugated diene. One has to do with allylic carbon chemistry. And the third one, which is the Nobel Prize winner reaction, that's called Diels-Alder reaction. In the alkene chapter that we learned in a previous course, we basically used hydrogenation reaction to figure out the stability of alkenes. And what we learned there, that the hydrogenation reaction is which is about using hydrogen in presence of a catalyst. It's an exothermic reaction. The more exothermic reaction it is, the more unstable the alkene that you trying to hydrogenate. So what we ranked in the alkene chapter, we say that we have the tetra-substituted alkene, which is the most substituted form of an alkene, will always be the one that's going to release the least amount of energy. And that's why will be the most stable alkene. Next would be the tri-substituted, next would be the di-substituted, and mono-substituted will be the least right after the ethylene, which is basically when you have a CH2, CH2. Now, we're going to use the same reaction, which is a hydrogenation reaction, to justify the stability of the diene or the conjugated systems. So what's a conjugated system? It's a bunch of double bonds that are separated by sigma bonds. So when you have a structure like this, for example, you have double bond and another double bond separated by a sigma. So that's a conjugated system. But when you look at this example, what do you have? You have a double bond and another separated by two sigma bonds. That makes it right away an isolated system or non-conjugated system, whichever of the two terms will mean the same thing. We will learn that there is some chemistry we're going to do in this chapter require the conjugated system to be in place. Otherwise, that reaction will not take place. So how come these systems are very stable? So using, once again, the hydrogenation reaction, which is, if I see a simple alkene, I will look at it as the mono-substituted one will give me a heat of about 126 kilojoule. The di-substituted one will give me about 114 kilojoule. So I can tell there that the di-substituted is more stable than the mono-substituted. If I combine the two alkene in one system, having this diene, I would assume that I will get the total of these two, which is about 126 and 114. Add them up, you will be expecting 240 kilojoule to be released in this reaction. But what's being released instead, 225 kilojoule. So let me repeat. If I take this and do hydrogenation, I will have 126 kilojoule released from the reaction. If I take this di-substituted alkene and do hydrogenation, I will get 114 kilojoule released from the reaction. If I combine the two in the diene system, which is a conjugated system now, I would expect that the energy to be 240 kilojoule released in this reaction. But what's happening in reality, the actual value is actually 225. So it's 15 kilojoule less. And that tells me that the diene is more stable than having isolated diene, isolated double bonds. The reason behind that is actually the p orbital overlap. We learned that the double bond usually consists of one sigma, one pi. The pi bond requires the overlap of two p orbitals, one p orbital from each side of the double bond. Having four p orbitals in this system, which is the diene system, will allow for the four p orbitals actually to overlap together. So we're looking at the overlap of the double bond p orbitals and the overlap of the other double bond p orbital, and there is a small overlap of the two sets of p orbitals. So it's like you're having basically an additional overlap between the two pairs of p orbitals, and that is actually something that's been proven with the sigma bond that's between the two double bonds. It's more of a partial double bond when the bond length been measured. So it's not a straight single bond. It's actually more of a partial double bond in there. And the only way to justify this phenomena is the overlap of the p orbitals in those double bonds. That provides the delocalization ability of the electrons within those two pi bonds, and that delocalization will stabilize the molecule even more. So that's the reason why you see the diene being even more stable than the predicted value of those double bonds, having each double bond treated separate, as we've seen in this example. So we could see here how, if we take examples of candidates for hydrogenation reactions, we see that the conjugated diene will be more stable than an isolated diene. And this isolated diene, the reason why it's more stable than the other isolated diene is because of the di substitution on one of them. The more substituted the alkene, the more stable it is. That's what we learned from the alkene chapter. So in this case, the more substituted diene will be more, the more substituted isolated diene will be more stable than an isolated diene that's not, that's less substituted. Alkyne would be next in terms of stability. The terminal alkyne will be less stable than an internal alkyne, and the most unstable structure will be the cumulated diene, when you have fused double bonds together on that system. You could see that it releases 292 kilojoule per mole versus 225 if those two double bonds are isolated by a sigma bond. This diene structure, it's very important in some of the reactions that we're going to learn in this chapter. And before we get into that reaction that we're going to learn in regard to the diene, we also have to keep in mind that this sigma bond in between the two double bonds allows for rotation in this system. So we should consider that the fact that it's a sigma bond, it will allow for rotation around it, meaning the two double bonds that are coming off this sigma bond could be trans, could be cis. So this word S, it stands for sigma. So any diene that's an open chain, that's not a ring, as we're gonna see, probably there are cyclic dienes. I'm talking about the open chain diene. Like in this case, is the beta 1,3 diene. You're always gonna have a rotation happening around the sigma bond that will basically go between the trans and the cis. And so you're gonna have the S trans and the S cis. Always keep in mind that the S trans, due to the less steric effect, less steric hindrance, will always be more stable by 12 kilojoules. However, this S cis is the one that's gonna be required in some other reactions that we're gonna learn in this chapter. So you're gonna say, okay, you're confusing me. Which of the two gonna really react? Isn't it the one that's gonna be more stable? Well, the more stable is the S trans, but you're gonna see in some of the reactions, which is in specific, is gonna be the Diels-Alder reaction, that the S trans cannot work in that reaction due to the fact that the two sets of p orbitals will not have a perfect overlap. It's like you're having two p orbitals overlapping here and two p orbitals overlapping on the opposite side. While in here, you're gonna have two sets of p orbitals where they're going to be actually on the same face. So that's going to actually help in the overlap of the two sets of p orbitals, therefore will help the delocalization, will help actually also the reaction to take place. That doesn't play a role in the stability. The stability will still be the S trans being more stable because of the less steric hindrance around that sigma bond. So that's one system we're going to be dealing with. The other system that we're going to be dealing with is allylic chemistry, allylic carbon chemistry. When we say allylic group, we're talking about a carbon that's an sp3 carbon adjacent to an alkenyl group. Every single time you see a system where you have a double bond, adjacent to a carbon that's an sp3 carbon, this sp3 carbon will become the allylic carbon. And there is some chemistry can actually take place on this carbon. Now keep in mind, this carbon can be positively charged, and that will be the cation, can be negatively charged, and that will be the carbanion, and it could be also the radical. And so that's why you're going to have three different systems out of the allylic group, that you could have an allylic cation, allylic anion, or allylic radical. Three different chemistry. So here's some examples. You have an allyl group, you have an allyl alcohol, you have the allyl benzene. In all of them, they share one thing, that is that they are stabilized by the resonance. And when I say all, I'm talking about the cation, anion, and the radical. They all are stabilized by the resonance. And here's an example. So if I take the allyl bromide and that halide kicks off, you're going to be leaving behind the carbocation. This carbocation is actually stabilized by this double bond. So every single allyl cation will always have two resonance forms. And this is something we learned actually in a previous course. Now this stability, once again, which is coming from the resonance, it makes the allyl cation more stable than regular carbocation. So if you would be ranking carbocations, you will say the methyl carbocation will be the least stable, next will be the primary, next will be the secondary carbocation, next will be the tertiary carbocation, and next will be the allyl carbocation due to the resonance. What's the most stable carbocation in all of the chemistry of carbocations? The benzylic carbocation. That's something actually been covered in a previous course. So this resonance, once again, it's actually reflecting also on the radical. So when you look at the radical, you will see that having that CH bond, once it's homolytically cleaved, you could see how it actually requires the least amount of energy compared to a tertiary, compared to a secondary, compared to a primary. So what I get out of this, that the allylic radical will be much more stable than a tertiary, than a secondary, than a primary. And the same applies if I would be dealing with an allylic anion. The allylic anion will be more stable than a tertiary anion, than a secondary anion, than a primary carbon anion, or the methyl carbanion. This is very important to keep in mind, that the resonance, it does give stability to those intermediates. So let's look at the very first reaction. That is 1,2 and 1,4 addition to conjugated diene. And we're going to take this as an example. The 1,3 butadiene, which is, as we said, it exists in the S form, S trans, and the S cis. So it's going to basically do that conformation, going back and forth between the two. Now, this reaction wouldn't matter whether you're dealing with a cis or trans, and we're going to see why that is. So if you are adding HBr to this diene, you would expect this to be added in a Markovnikov fashion. What's the Markovnikov addition? Markovnikov addition tells me that when I add an electrophile to an alkene, hydrogen goes to the carbon that has more hydrogens. So if I have HBr being added to an alkene, the very first thing is going to happen that the hydrogen will go to the CH2, not the CH. So the Br will be actually be placed on the internal carbon, of that alkene, and that's what you see here. So you have basically a hydrogen added to the terminal, Br added to the internal. But how come I see this product? Where did this come from? Well, the only way to justify why I have two products adding HX to a diene is through the mechanism. And the mechanism is very simple. Keeping in mind the Markovnikov addition of HX to an alkene, where the hydrogen should go to the carbon that has more hydrogens, I should just remember that to apply it here. Having an alkene, either of the two alkene won't matter to use because both are similar. So if I use this alkene and I attack HBr, it will attack the hydrogen, kicking off Br minus. Which of the two alkene carbons is going to pick up the hydrogen? The terminal one, the one that has more hydrogens. So that's why you see the internal carbon now it's becoming positively charged. What am I dealing with? I'm dealing with an allylic cation. I know already that any allyl cation will have a resonance. So what's the resonance form of this? Will be basically the delocalization of the double bond to satisfy the plus charge, leaving the plus charge to be on the terminal carbon now. So I have two allylic carbocations, but they are not the same. What do I mean? I have a secondary allylic carbocation versus a primary allylic carbocation. And that makes the two are candidate for the next attack by the Br minus, because the Br minus can attack the second carbon or it can attack the fourth carbon. So when it attacks the second carbon, once you add the hydrogen to the first, then it's going to give me the 1,2 addition. And that's what I see here, that the Br minus is attacking the carbon number 2. Once the carbon number 1 picks up the hydrogen, carbon number 2 being attacked by the Br minus will give me the 1,2 addition reaction product. If I have the primary allylic carbocation, which is going to be formed by no choice, it will be formed because of the resonance delocalization. This carbon now will be attacked by the Br minus to give me the 1,4 addition product. How do I know which one to write down in a chemical reaction? It's going to depend on temperature. It's been observed that this reaction, which is the diene plus HX, and most of the time you will see HBr or HCl. Least common to find HI or HF to be used in those reactions. It's very common to find HBr or HCl, as they are more energetically favored. So if you have this reaction done at temperature that's below 0, you will notice right away that the 1,2 addition is going to be the more favored product, and we will justify that. And if it's done at temperature higher than room temp, you will see the 1,4 product will be the one that's going to be more favored. So how come the 1,2 addition is more favored at low temperature and the 1,4 addition is more favored at high temperature? The reaction intermediate or the reaction energy diagram will justify this, knowing that we have an allylic carbocation that will go back and forth between the primary allylic carbocation and the secondary allylic carbocation. Keep this in mind. Now, in order for the reaction to get to the allylic carbocation, that will require its own activation energy. Once I am there, now this primary carbocation, primary allylic carbocation versus the secondary allylic carbocation, they're not going to have the same activation energy getting to the product. Meaning, if I have the secondary allylic carbocation, which is this one, it's going to require less energy to get to the product. Why? Because the secondary allylic carbocation is more stable. Versus the primary allylic carbocation will require more energy to get to the product. So we could see here that the stability of the allylic carbocation will actually determine how much energy needed to get to the final product. So what do I get out of this? I get that the 1,2 addition is the faster to form. And that's why it doesn't need energy. And that's why this product is the kinetic product. What does kinetic mean? Faster when it comes to chemical reaction rate. This product, which is the 1,2 addition product, is coming from the secondary allylic carbocation. And this secondary allylic carbocation is more stable than the other resonance form, the other allylic carbocation, which is a primary. So the faster one to form will be actually the one that's labeled the kinetic product. How about the second one? The other one, which is the primary allylic carbocation. This primary allylic carbocation, due to the fact that it's less stable, it will require much more energy compared to the other route, the 1,2 addition route. This 1,4 addition ends up with a product that is actually more stable. So when you look at the 1,2 addition product, you're going to notice it's a monosubstituted structure, monosubstituted alkene. How do I know it's monosubstituted? Look at the alkene and look at how many carbons coming off this alkene unit. Only one. So that's why it's a monosubstituted alkene. The other one, look at the alkene. You have two carbons coming off that alkene. So that makes this alkene a disubstituted alkene. And because it's a more stable product, will be labeled the thermodynamic product. So why is it labeled the thermodynamic product? Not because it's faster to form, not because the intermediate is less reactive or less stable, it's because the final product is more stable than the other product. So as a summary for this reaction, we can say the following, that the addition of HX, whether it's HCl or HBr, to beta 1,3-diene will always generate a carbocation. This carbocation will be an allylic carbocation. You will have a secondary allylic carbocation and you will have a primary carbocation, allylic carbocation. The secondary allylic carbocation will generate the 1,2 addition. The primary allylic carbocation will always generate the 1,4 addition. Lower temperature will favor the 1,2 as it is the faster product to form. It is the kinetic product. 1,4 addition, the one that's coming from the less stable intermediate, will always be forming the more stable product, the thermodynamic product. That's very important to keep in mind, and that will always happen at higher temperature. In order for me to ask a question on an exam or a quiz, I have to indicate the temperature. So all what you need to figure out, all right, is it a lower temperature than room temp? Then it will give me the 1,2 addition. Is it higher temperature than room temp? Then it will give me the 1,4 addition. These percentages are not required from you to know due to the fact that you're going to have to do the experiment in order for you to figure out what the percentages of those products are. Allylic carbon chemistry. One of those chemistry is actually the allylic bromination. So what I mean by this, having an allylic system will basically go through a bromination step to give me the allylic halide at the end. This is a chemistry that we learned in one of the chapters in Chem 211, where we can have an alkane reacting with Br2 and presence of light or heat will give me basically the most stable carbon radical to be the one that's going to pick up that halide. And that's how we do the alkane halogenation. In the case of an allylic halogenation, keep in mind, you don't touch the alkene, rather you touch the allylic carbon to be the one that's going to be halogenated. So just to show you basically in brief what this chemistry is about, this reaction will go through some initiation. So the the Br2 will be going through a homolytic cleavage to give you 2 Br radicals. One Br radical will basically abstract the hydrogen from the allylic carbon. So that will form HBr, leaving behind an allylic radical being stabilized by the delocalization. And this allylic radical will then basically form a bond with one of the Br2 to end up having the allylic bromide at the end. Now, in order for this reaction to be controlled better, we tend to use NBS. N-bromosuccinimide has been known actually to be used specifically for allylic halogenation. So what you are required to know that every single time I have an allylic carbon, I could actually halogenate it using Br2 with light, or even better, NBS with light. So the NBS basically is better in terms of regioselectivity and controlling due to the fact that it releases Br2 very slowly while the reaction is taking place. Meaning, instead of injecting Br2 in a high concentration, you will be injecting NBS instead, and that will actually control the halogenation of that allylic carbon to be monobrominated structure rather than a dibrominated or multiple bromination taking place on every single allylic carbon. So this is very important reaction to keep in mind. And as we see here, the delocalization of the allylic radical will actually provide even more halogenated product if that allows. Meaning, if I have this structure, whether I brominate this or I brominate the other, that's not going to change the chemistry of it. So meaning that if I have this allylic radical or that, if I place a Br here or I place a Br over there, these two structures will end up having the same product. However, if I'm dealing with a molecule like this, and I generate the radical on this carbon, this radical can actually be stabilized with the pi bond. So the delocalization will generate another resonance form that's different from the other. So these two are going to be giving me two different products. So every single time we're dealing with an allylic carbon, we want to make sure that the two resonance forms are not the same, because if the two resonance forms are exactly the same, like this, then we're going to end up having the same exact product. So this is important to keep in mind, that when we deal with allylic halogenation, if the structure of the resonance of the intermediate, which is the allylic radical, does give me a resonance form that's different in terms of structure, then automatically I need to keep in mind that I have to actually account for the formation of two different products, and that's what we see here. Here we see a bromination happening on this allylic carbon. Here we see a bromination happening on the other allylic carbon. So a primary allylic versus a secondary allylic. So definitely we're not going to have the same exact product at the end. Okay. The other chemistry that could also happen on the allylic carbon is the SN2 chemistry, meaning having an allylic carbon with a halide attached, I could actually have a strong nucleophile substituting that carbon. So as an example, we could probably see this. So having a nucleophile that's a strong nucleophile, could be CN minus, could be RO minus, could be anything that is a very strong nucleophile. This will basically allows for the SN2 to happen very fast when we deal with an allylic carbon, due to the fact that this CX is being actually weakened by the allylic delocalization, and that the presence of the pi bond next to that carbon being substituted is going to allow for the SN2 to happen even faster. And that's what we see when we compare primary to secondary to tertiary to a methyl X. When it comes to SN2 reactions, we see the allylic halide going to be faster than actually doing a secondary or tertiary halides. So that actually contributes, once again, due to the fact that you have stabilization because of the double bond, it helps in the formation of the SN2 product at the end. Same applies if I would be using weak nucleophile. If I'm using a weak nucleophile reacting with an allylic halide, I would expect an allylic carbocation, and that allylic carbocation will then give me the SN1 product. So allylic chemistry could be allylic halogenation, where you see the radical being the intermediate, SN2, where you see basically a concerted mechanism, very straightforward substitution of the CX by a strong nucleophile, and SN1, where you see that CX being basically cleaved to form a carbocation. That allylic carbocation will then undergo attack by a weak nucleophile to give me the SN1 product. And that's all what I wanted to talk about the first part of chapter 15.